This is 2018 AIME II problem number 15, and here is a view of this problem. We would like to find the number of functions f defined on integers with integer values such that f of 0 is 0, f of 6 is 12, and further we know that our function f satisfies this condition. What's the meaning of this condition? Well, the meaning is that the values of f will be such that the distance, if you will, between f of x and f of y would be squeezed between the distance between x and y and the distance between 3 times x and y. So the absolute value can be interpreted as distance in that sense. Okay, so does that make sense? Just to make sure everybody is on the same page, one idea is to substitute x with n and y with n minus 1. So we are considering consecutive entries. So for consecutive values, what can be this difference, this distance, right? So for instance, f of n minus f of n minus 1 for these two consecutive entries in absolute value would be between, well, n is greater than n minus 1, so we no longer need absolute value on the left hand side. n minus 1 is just 1, and 3 times n minus 1 is 1 again, so 3 times, so it's between 1 and 3. What it means is, so just to give you an idea, I can think of it like the following. So I can just put the x values here and f of x here. So 0, 1, 2, 3, 4, 5, sorry for that, and 6. So we know that f of 0 is just 0, f of 6 is 12, and now the nice part. So as I move from 0 to 1, so as I move, my value increases from 0 to 1, I'm told that my functional values in absolute value will range between 1 and 3. The meaning of this is they can either increase, so as you move from one to the other, they can either increase by plus 1, plus 2, plus 3, or they can decrease by minus 1, minus 2, minus 3. Does that make sense? At each step as I move in that direction. Does that make sense? We can also have a look at what happens if it's not consecutive, but what if they are separated by 2? Then their distance is equal to, so n minus 2 is just a 2, and that has to be 2 times 3, which is 6. Does that make sense? So, and then you can do the same thing if the gap is 3 and so on. So what we are saying is, so during this gap, as we go from 0 to 1, this value here would have to be either plus 1, plus 2, plus 3, or minus 1, minus 2, minus 3, and so on. An acceptable sequence would be something like, for instance, you can go up by 2, and then you can go down by 1, and then I can go up by 3, I guess. I don't know. Even this is not acceptable, by the way. Sorry, I can go down by 1. Sorry. Yeah, it's still unacceptable. Why is this unacceptable? Well, it satisfies the first condition, obviously, but it fails the second condition, because as you compare 0 and 2, according to this description, the minimum gap should be at least plus 2. Or minus 2 in that sense, so plus or minus 2, so or either between plus 2 and plus 6, or between minus 6 and minus 2, right? So but 1 is not such a number, so that's not gonna work, right? So does that make sense? So let me just delete that. So between consecutive entries, you either increase by plus 1, plus 2, plus 3, or minus 1, minus 2, minus 3. Every 2, if you increase by 2, I mean the x value increases by 2, then your y value increases by plus 2, plus 3, plus 4, plus 5, plus 6, or minus 2, 3, 4, 5, 6. Does that make sense? So there's only so many values that are acceptable in that sense. So that's my first observation. The second observation is, because I need to eventually increase in value, right? I cannot make use of too many minuses, right? So my value cannot decrease too many times, because eventually I want to increase, and incrementally as I go from one step to the other, I can only increase at most by 3. So that already gives me a kind of a restriction on the number of times that value can decrease as I go from 0 all the way up to 12. Does that make sense? So for that reason, let's quickly check the following very conservative situation. Suppose that we increase by, say, 3. This is the max we can increase. Then in the next step, so I increased by 3. Then in the next step, I will decrease by, in a very conservative fashion, just by -1. And then even though I increase by 3 again, so up to 5, when I increase one more time, so if I have 2 decreases, so I'm at 4, and there is no way I can recover from this situation. So I add 3 to this would be at most 7, and the gap here is 5. Do you see that? So that's a critical observation. We can go down by at most 1 time. And that gives me an idea for working this problem as a casework. We did the main thing of the problem, that was the critical part. So let's solve this as a casework. So we have 2 cases. The first case, we only go up. So how many? So you start from 0 and you go up 1, 2, 3, 4, 5, 6 times, and eventually you go all the way to 12, right? So how many? So you have 1, 2, 3, 5 numbers in the middle. How many ways can you arrange these numbers? For instance, a potential sequence would look like, I don't know, maybe 2, 5, 6, and something like that, 8, 10, and 12. So how many of these, how many ways can I arrange the numbers, the integers between 0 and 12, such that each gap is increasing, right? So we keep increasing, and that's it. Arguably the easiest way to think about this is to count. So therefore we are only allowed to use gaps of 1s, 2s, and 3s. Let's say that the number of 1s is equal to A, the number of 2 gaps is equal to B, and the number of 3 gaps is equal to C. So for instance, in this particular example, we had a B here, we had a C, an A, another B, another B. So we used 3 B's, 1 C, and 1 A. But what's the general condition for this type of situation? Well, in total we have 6 gaps, so the sum of A plus B plus C items is equal to so it's equal to 6. But then each gap, so for each A gap contributes 1, each B gap contributes 2 times, and each C gap contributes 3 plus 3. We want to start from 0 and reach to 12, and that's it. That's all we need. So from here, this would imply that, for instance, if you multiply the first equation by -2 and add it to the second equation, you would get minus A plus C is equal to 0, implying A is equal to C. And you can even further, for instance, subtract the first equation from the second equation, and you will also get B plus 2C is equal to 0. So these should be sufficient, more than sufficient actually. Even the very first one would have been sufficient to establish the potential solutions. And this is one of the, sorry, this one is one of them, obviously. A, B, C. Let's see if we can find them. So A and C must be equal, so they can both be 0. In that case, B would be 6. Does that make sense? Because did I mess up? Of course I did. This was a 6. I just subtracted this one, first one, from the second. I should have a 6. Okay. The next I can have A and C be 1, and B as a result would be 4. Or A and C can be 2, in which case B would be 2. A and C can be 3, and B would be 0. And that's it. This is all the possible ways we can get we can have this sequence of increasing numbers, right? So how many ways to arrange these numbers? So it's 6 factorial divided by 1 factorial, 6 factorial, 1 factorial, which is just one way, right? So you have 6 increases of 2's, right? So it would, our sequence in that case, for example, just to give you an idea, our sequence would look like 0, 2, 4, 6, 8, 10, 12. So we have B, 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 and B. That's it. How about this one? That one is just 6 factorial over 1 factorial, 4 factorial, 1 factorial, so which is just 30 different ways to arrange 1A, 4B, and 1C. How many ways to arrange 2A's, 2B's, and 2C's? 6 letters, 2A's, 2B's, and 2C's. It's 6 factorial over 2 factorial, 2 factorial, 2 factorial. 6 factorial is 720, divided by 2 is 360, divided further by 2 is 180, divided by 2 is 90. And finally, this one, 6 factorial over 3 factorial times 3 factorial, which is 5 factorial over 3 factorial, which is 20. So you add these 120, 140, 141 different sequences for case 1. Now we are in case 2. Okay, case 2 is slightly more involved, but still not too much more. So case 2 is the following case. So again, we start, so we have our x values and f of x values, 0, 1, 2, 3, 4, 5, 6. We have established that this time there will be one decline, one decrease. For example, let's say that the decrease is over here. So what can happen? We know that we have to start at 0 and we have to end at 12. And now remember our early on observation, right? So this is a critical observation that needs to be satisfied. For instance, can we have a situation something like we increase from 0 to 2, then we decrease back to 1, and so on, and then we increase by 3, let's say. Is this possible? Well, the answer is no. Well, obviously this sequence satisfies the first condition of increasing or decreasing by +1, +2, +3, and -1, -2, -3. However, so the gap here is +2, then -1, then +3. So it satisfies the first one, but it doesn't satisfy the second one in the following sense, in the sense that as you go from here to here, remember that if in this case it's increasing from 0 to 1, the increase should be at least by +2, and this doesn't satisfy that. So as a result, this is unacceptable. Because the increase must be at least by 2, it already gives me a pretty good idea what can happen, right? So this guy has to be 3. Does that make sense? And then you can move further, right? Actually, it also let's see. Actually, I can do better than that. I can now apply some abstraction. Let's see if I can I can think of some abstraction. Let's say that the decline happens here, and let's say that this number is n, and we established that after the decline, I should be careful, the gap between these two must be at least 2. +2, I should say. So as a result, this can be n-1, and this one has to be n-3, right? Because I can increase by 3 and then decrease by 1, so that the increase is still 2. Does that make sense? But then as I move from here to here, I will be careful again, because the gap here must also be at least 2. But again, from n-1, the most that I can do is n+2, and boom. So therefore, we are already binding ourselves, right? So there's so many restrictions. 4 of the just knowing where the decline will happen, in this case between 2 and 3, it already fixes everything between those steps, right? Does that make sense? So what's interesting is, whenever you know where the decline is, the 2 elements before it and the 2 elements after it are fixed. So this gives me 2 subcases in that sense, right? So 2 subcases that I can work on. So the first subcase is, because the 2 elements before will be affected, the most that I can take this arrow would be to the left. Like it will be, so okay, so the down arrow is at between 1 and 2, or between 2 and 3, or between 3 and 4, or between 4 and 5. Does that make sense? And then case 2 by 2.2 will investigate what will happen if the decrease is between these two or between these two. Does that make sense? So as a result, look at how much we are covering here. Okay, so let's change the color again. So we are covering from n-3 all the way up to n+2. So we are covering 5 space, right? Out of the 12, 5 of them is already covered. How many gaps left? 1 gap here, 1 gap, 3 gaps in total, right? We have 3 gaps left, and we need to cover 5 spaces are already covered, so we have 7 more spaces to go. Does that make sense? So in that case, our equation now would look like a plus b plus c, huh? So we have, like we said, we have only three gaps left. Remember that a is gaps of length 1, gaps of difference 2, and gaps of difference 3, right? So therefore a plus 2b plus 3c, we still have to cover 7 more spaces, and that's it. Like we did in the previous question, we can easily solve this. For instance, if you subtract the first one from the second one, that one will give you b plus 2c equals 4. And then you can, like we did in the previous question, we can multiply the first one, say, by yeah, we can do that. I guess we can multiply it by minus 2 again. So that will give us, well, it's not as clear as the first one, but even here we are pretty much, we know how to handle it, right? So we need to find numbers which satisfies these two conditions. So let's just keep it like this. So therefore we need a, b, c. Okay, so what are the potential solutions? If b, let's start with c. If c is 0, then b is 2. No, b is 4. Oh, that won't work. Right, because the total, okay, so c can never be 0. So c is 1. In that case, 2c is 2. So b is 2. And as a result, a is 0. Yes. An alternative would be if c is 2, in which case b is 0 and a is 1. That's right. This is all that's possible in this case. So therefore, sorry for that, some tea. How many ways can you arrange 2b's and 1c? 3 different ways. How many ways can you arrange 1a and 2c? 3 different ways, for a total of 6 ways. So this case produces 6 choices, and well, depending on, we have 4 subcases here, right? So we are either in this case, in this case, in this case, or in this case. So we have 4 choices. So 4 times 6, each one produces 6. So we have 24 solutions in this one, 24 ways. From the previous one, we got 141 ways, remember. Okay, lastly, case, oh my god, terrible handwriting. Okay, case 2.2. Well, in this case, it is slightly different than the previous one. 0, 1, 2, 3, 4, 5, 6. F of x start at 0, end at 12. However, now the decline is, say, here. Okay, the same rule will apply. The gap between these two, eventually we know we will increase here, right? And the gap here has to be at... can we go down by -3, for instance, and then go up by 1 so that we are -2? I think -2 is acceptable, right? And then keep increasing by 3. 1, 4, 7, that's not allowed. So this case is out of the window. Okay, so therefore the only possible case is I have to be a +2 here. So therefore this one is a -1. So there's a decline, and then we keep increasing 2, and that's it. So we have pretty much freedom in these 3 places here. Does that make sense? So therefore, in total, I need to cover 1, 2, 3, 4 gaps. A plus B plus C is equal to 4. And the distance I need to cover, A plus 2B plus 3C, is equal to 10. That's it. And it turns out that if you put that down arrow between 5 and 6, it will give you the same. So I will, whatever I have, I will multiply this result by 2. So don't forget to multiply by 2. Well, I'm telling myself. Subtract first equation from the second. We'll get 6. And then the total, let's use the total, is 4. So therefore, ABC, finally, we can have, well, like we did in the previous case, we can have C is equal to 0, in which case B is equal to 6. That's not gonna work. C is equal to 1, in which case B is equal to 4, A is equal to 0. C is equal to 2, B is equal to 2, A is equal to 0, and C is equal to 3. Yes. B is equal to 0, and A is equal to 1. I believe that's all the potential cases for this one. Oh, this one adds up to 5. Oh my goodness. Okay, so that's definitely wrong. Okay, so therefore, how many ways can we arrange 2 C's and 2 B's, right? So 4 letters, so 4 factorial over 2 factorial, 2 factorial. 4 factorial is 24. Divide by 46 ways here. And then this one, how many ways can we arrange 4 letters? 1A and 3C, 4 different ways. So you add these two, you will get 10 ways here. But remember that the arrow, don't forget the times 2, the arrow can be here or here, so we have times 2, which is 20 ways. And that's it. So case 1 plus case 2.1 plus case 2.2 will give us, so these are different cases. So case 1 gave me 141 solutions, case 2.1 gave me 24, and case 2.2 gave me 20 different solutions. So that would give 16185, is it? Yes, it is. So 185 is the correct answer, and hope to see you guys in our next lecture.